In this example, we're asked to look at the frame, which is shown below. That frame is made up of three lengths, EC, BD, and AC, joined together as shown there in the figure. There's a uniform load of W0 acting all the way across link AC. And what we want to do eventually is we want to make a cut through member AC there at G. And we want to expose and calculate the internal axial force, the internal shear force, and the internal bending moment acting on the left face of that cross-section there at G. So in this problem, we have to do this in steps, which is very common of the kind of problems that we are facing here. So the first step is to find the external reactions acting on the entire frame. So as I draw my free body diagram of the entire frame, the forces that I have acting on this, there's going to be a pair of components of reactions here at E. It's going to be EX and EY. There's going to be a roller force which is acting on in there at A, which I'll call just a normal force in A. And then there's going to be a resultant force F from that constant, the uniform line load of W0. It's going to be at a distance of H to the right of there. And let's write down some trig. This angle here, that angle I'm going to call that a theta. That's the same angle as the angle on which that roller rides. And I think that that's it. So whenever, well, I guess I do need to write down what F is. F is the resultant force, and that's 6, the base, times the height, W0. H, it's a uniform load, so it's going to be at the midpoint, which is at 3 feet. What I'm going to do is write a single moment equation about end E for this frame. As I resolve NA into its components, its vertical component is going to be NA cosine of theta. That's going to have a moment arm of 6. It's going to be in the negative K. As I look at the horizontal component, which is NA times sine theta, it too will have a moment arm of 6, and it also is in the negative K. And then I have the moment about E due to the load F. It's got a moment arm of H. It's in the positive Z. So when I set that equal to a 0 for equilibrium, I solve for NA. NA is the resultant force F at this distance H divided by 6 cosine theta plus sine theta. So we have all the numbers it takes then to calculate NA. So that's the first FBD. The second FBD I'm going to draw is one of AC. So this again is going to be A, and B is the point there in the middle, and then C. So the forces that I have acting on this member is still going to be the normal force there of NA. It's going to be acting at the angle phi, which I defined before. There are the pin reaction forces there of CX and CY acting at joint C. There's going to be the load here is 6W0 acting again at a distance of 3 feet to the left there of C. And then now we have the load that's carried by member BD. Well, BD is a two-force member, so the load it carries is along the direction of link BD. So this is going to be at an angle which I will refer to as phi, where phi from trig here is the inverse tan of 4/3. So that's the FBD that we're going to use. I'm sorry that I have mislabeled this angle here. I call that phi when above it was defined as a theta. Theta is the 60 degrees. From this FBD, what I'm going to write down is the summation of moments about C. And when I do a moment equation about C, the load of 6W0 that has a moment arm of 3, it's in the positive case, so that gives a plus sign. The force of FBD, which I drew but failed to give a name to, FBD is that. It's going to be FBD sine phi. That has a moment arm also of 3, but that's in the negative K. And then I have NA. The Y component is NA cosine of theta. That will have a moment arm of 6. The X component of NA acts through point C, so it doesn't cause a moment about C. So that sum for equilibrium is a 0. So from that, I have calculated now the load that's carried by member BD. That will be 18W0 minus 6NA. We just calculated that as cosine of theta, divided by 3 sine phi. At this point, we know everything that goes into that equation, so we can write down a number there for FBD. That was our second free body diagram. Now, our eventual goal, which we are working on right now, is to find the internal force couple there at G. So my third FBD is to draw a free body diagram of the section which remains when I had cut AC there at G. The forces, well, we still have the normal force that's acting at A. We call that NA, and that was at an angle of theta. We have a resultant applied force, which I'll call lowercase f. It's going to be at a distance of lowercase h. I'll define those below. Keep in mind we still have our load of FBD acting on member AC, or at least that section of AC. And then at G, what we want to find is the shear force, VG, the bending moment, MG, and the axial load there of FG. Where the applied force F, that's the magnitude of that line load, W0, times the distance, the length of beam over which that acts. In this case, it's 4.5. H is going to be half of 4.5. It's in the middle of that cut section. So therefore, from this FBD, I can write down 3 equations. One, I'm going to sum the forces in X. I get NA sine theta. I have a minus FBD, and this angle again is phi. FBD times cosine phi. I will have for the X component also FG, one thing we're trying to find. And for equilibrium, that sum is a 0. So the internal axial load FG is equal to FBD times cosine phi minus NA sine theta. We've already found all these from above, and that's why we do this, is that so at this point we have the internal axial force there of FG. Summing forces in Y. Summing forces in Y, we have NA cosine of theta. I have plus FBD sine phi minus the applied force F and minus the way I drew my shear force VG is a 0. So from this, we solve for the internal shear force there of VG is being NA cosine theta. We know that one. FBD, we know that, times sine phi, minus F. And so that sum there on the right-hand side gives us VG. And therefore, we have all the numbers it takes to get the answers. So what I'm going to do lastly here is do a summation of moments about the right end G. Summing moments about G, I have FBD times sine phi. That force about G has a moment arm of 1.5. The applied force F, that is a moment arm of H, that's a plus sign. We have minus NA times cosine of theta. That's the y component of force, has a moment arm of 4.5. And that's a negative sign because it's in the clockwise direction. And then the internal bending couple there of mg, that is a 0. So from this, we calculate mg. mg is minus 4.5 FBD sine phi minus F times H plus 4.5 in a cosine theta. We have everything that we need to calculate mg. So again, our goal was to find the internal force couple set there at G when we made a cut through G. In order to get to that point, though, we had to do 2 steps before. The first thing we had to do was find the external reactions there at points E and A, in particular there at A. The next thing we did, we isolated AC. The reason we did this is we needed to find the load of FBD on section AC. Once we had that, then we did what we really wanted to do, and that's a free body diagram of the section of the beam cut through G, which exposed the internal shear force VG, internal bending couple there of mg, and internal axial force there of FG. From equilibrium equations we saw for those 3 unknowns.